Welcome to our talk on our CVPR paper, Ground Truth-Free Meta-Learning for Deep Compressive Sampling. Compressive sampling, CS, is a popular technique for imaging. Recently, an increasing attention is paid to the unsupervised training of deep networks for CS image reconstruction. The unsupervised external learning and test-time internal learning approaches have their pros and cons. Thus, we develop an unsupervised meta-learning approach to marry their advantages. The framework of our proposed approach includes two stages. First, train a model via meta-learning using only CS measurements. Second, adapt the meta-trained model to a test sample to exploit internal characteristics. The challenges are twofold: noise suppression for range space learning and zero information for null space learning. We address these challenges by developing new loss functions and improving the meta-learning process. Also, we investigate new NN design for improvement, including an iSure loss for meta-learning and adaptation, which allows efficiency noise-resistant range space learning, an iSure-based unsupervised MAML scheme, an ensemble-based inner loop for better null space learning, including an iSure loss for meta-learning and adaptation, which allows efficiency noise-resistant range space learning, and bias tuning scheme for unrolling CNNs, which significantly reduces the parameter number in adaptation. The effectiveness of our method is demonstrated on MRI and natural image reconstruction. Now, let's dive into the details. Compressive sampling, or called compressed sensing, CS, is a popular technique for imaging. For a latent image X, CS applies a measurement matrix, phi, to capture a small number of noisy linear measurements, with measurement noise epsilon. The latent image is then reconstructed via solving X from the equation, y equals to phi X plus epsilon. Such a technique has a wide range of applications such as single-pixel cameras and fast magnetic resonance imaging. In recent years, there is an increasing interest in unsupervised training of deep neural networks for CS reconstruction, that is, using data without ground truths. Currently, there are mainly two types of approaches in this field. One is the end-to-end unsupervised learning, which performs external learning on GT-less datasets, and the other is using an untrained network to fit a test sample directly for internal learning, which does not access any training sample and thus is GT-free. These two types of GT-free learning have their pros and cons. This inspired us to develop an unsupervised meta-learning approach to marry their advantages, that is, exploiting large datasets for external knowledge learning and meanwhile exploiting characteristics of test samples for reducing dataset biases and negative effects of out-of-distribution. Given a training dataset with only measurement samples yj and the measurement matrix phi, the framework of our proposed approach includes two stages. First, train a model via meta-learning using only CS measurements. Second, adapt the meta-trained model to a test sample to exploit internal characteristics. According to the range null space decomposition, the challenges here are twofold. First, suppressing noise in the measurement samples on the range space of a joint of phi during training and adaptation. Second, learning reconstruction on the null space of phi on which no information is encoded by the training samples. We address these challenges by developing new loss functions and improving the meta-learning process. Also, we investigate new NN design for improvement. Our approach has four key components. Firstly, an improved Stein's unbiased risk estimator, iSure, is proposed for meta-learning and adaptation. Second, by incorporate iSure for range space learning and an ensemble inner loop for null space learning into model-agnostic meta-learning, MAML, we develop an unsupervised MAML scheme. Third, we develop null space consistent loss for improving model adaptation on null space prediction. Lastly, based on an unrolling NN architecture, we proposed a bias tuning scheme to accelerate the model adaptation process. The proposed iSure injects a noise term into standard Sure defined in range space, which provides robust estimation in the range space. The noise injection not only mitigates overfitting in GT-free meta-learning and model adaptation, but also allows ensemble in learning and inference. In addition, as shown in Theorem 1, compared to standard Sure, which involves MCMC for gradient update, iSure is more efficient with an explicit form of the gradient update step. We incorporate the iSure loss into standard MAML for unsupervised meta-learning. The iSure measures errors on range space for range space reconstruction learning, while the ambiguity on null space is addressed by the implicit prior from the network. For improvement, we introduce an inner loop with an ensemble loss, so as to leverage ensemble of predictions to improve the prediction accuracy on null space. During adaptation, iSure loss also only focuses on range space prediction. It may bring negative effects to null space prediction. We propose a null space consistency loss to mitigate those negative effects, which enforces the null space prediction not to differ much from the original one after model adaptation. To accelerate the model adaptation process, we employ an unrolling CNN for CS reconstruction and propose the bias tuning scheme, which only adapts the bias parameters, a small portion of the DNN's parameters. The rationale behind is, when viewing an unrolling CNN acts as an iterative shrinkage process, the biases play a similar role to the thresholds of shrinkage, which are critical for the success of the reconstruction. We conduct performance evaluation on two tasks. One is MRI, and the other is natural image reconstruction. On both tasks, our method performs noticeably better than existing GT-free methods overall, and it also competes against supervised methods including its supervised counterpart. Here are the comparison on computational complexity. Compared to the latest adaptation method DDSSL, ours takes only around 1/7 time. In addition, our bias tuning scheme significantly reduces the number of parameters being adapted. We conduct ablation study on each component of our approach. The results shown that each component has noticeable contribution to the performance. We also test the effectiveness meta-learning and model adaptation. From the results, we can see that meta-learning leads to faster and more effective model adaptation, and it also supports the adaptation to unseen measurement matrices. That's all. Thank you.